probably understand the. Yeah. Yeah. Okay, we should, I think, start the
Sure.
lecture. Yeah, so we have Venkat Abhignan from NIT Trichy with us, who will be speaking on blackbody radiation. And Venkat has been attending Sphics talks recently. And he has also been working on projects with Prachi and me recently. So thank you, Venkat. And
Thank you. Yeah, I should thank for all this beautiful opportunity and everything talking. Yeah. So yeah, I'll just get into what is blackbody radiation. I think you keep the camera so that you can show me the show us the
yes.
device at hand, not the device, the material at hand.
Yeah.
So basically, this is a small demonstration on what I'm going to talk about, and this can be imagined as a blackbody, and oh, you touched it with. He's touching it with cold water. So when the temperature is reducing, the body is emitting radiation green, and then as it goes colder, it is becoming red. So this is basically what you can think of.
I cannot see anything that's happening.
Yeah,
you're trying to show something.
Yes. So that's why initially it's in violet in color.
No, I cannot see anything.
Oh, Sajesh. Okay, I don't know. I'm not doing it. Shajesh sure is doing it.
Oh,
no.
You have to look at my camera.
Oh yeah, I don't know. Yeah. And Shajesh shows.
Yeah, maybe you have to pin it.
Yeah. Got it now. Okay.
Yes,
Got
yes,
it.
If you're using a phone, then you have to, I think,
saw it.
swipe.
Yeah. So what he did is he touched it with water so that it's cold, and he applied it on the back of that material. Initially it was in violet in color, and then it slowly turned green, and then it started turning red in color, which is essentially what we are going to talk about. That is a blackbody, a temperature dependent radiation giving output material. That is what I'm going to basically talk about. So I'll start using the board. So yeah, we will begin with seeing how we can picture this. There was this diagram in back of the board in Sphics, but I don't think anyone saw it. Yes, so I can just, this will be the energy density, energy output, and this will be the wavelength lambda. So what we saw here was, this is some T3 at a higher temperature, and this is a T2 and at a lower temperature. We saw that for higher temperatures, it was in violet or something, and as you go lower, it turned green and then red for lower temperatures. So we can, with this, have a ideal law which is called Wien's displacement law, which shows that this lambda max, or wherever the peak in the energy density is happening, times the temperature is some constant, which is B or something. And so this is basically the Wien's displacement law, and this is the basic idea of the blackbody radiation. We'll be trying to see this using thermodynamics. And so why are we using thermodynamics here? Thermodynamics is basically a macroscopic description of material. materials, or you can say basically if you see a gas, ideal gas in a container, let us suppose, and the ideal gas equation which I'll be using, where P is the pressure of this gas imparting on these walls, and V is the volume of this container, and N is the number of particles in this in this container. K is a constant, and T is temperature of this gas. This is the ideal gas law essentially. And so this is a macroscopic description which can explain for any gas. It can be O2 or N2, irrespective of whatever gas is in this container. These laws are obeyed. So what happens is we kind of do not need a microscopic description of whatever this gas is. We are not interested if what is the interaction between this O2 and O2, and then what is the interaction between this O and O molecule, and what is actually happening within the O molecule. All these microscopic description, microscopic interactions, we can neglect them and we can just go for a macroscopic behavior. And this is one of the reasons you can use thermodynamics for this explanation. And so we'll be using the thermodynamics first law, which is basically energy conservation. And then we'll be using the zeroth law and the second law. Hopefully, yeah, this information I'll be able to impart the first law, zeroth law, second law. But before that, I'd just like to say that when you try to go from a microscopic description to this macroscopic kind of behavior, we need, this is basically the energy conservation, and this needs that N is very larger than 1. Which means there are large number of particles in this container. And so this is the basic preliminary, whatever I wanted to say. And I'll go for whatever this first law is, second law is, and zeroth law is. So zeroth law basically is that if I take a adiabatic container with 3 partitions, adiabatic here is that this wall is thermally insulated. How do you make it thermally insulated? You use mirrors, and you can, so that you trap the radiation, and then you can use vacuum so that there is no escaping of materials from here to outside. And the gas is filled in this first container, and then you somehow remove this partition, first partition, so that the gas is distributed in the 2 containers, such in the same adiabatic setting. Adiabatic here means thermally insulated. And then again, after, and you set it again, you vanish, remove even this partition. The gas is now distributed all over this container. Essentially, in this process, what we can say is that,
Venkat, just a quick
Yeah.
clarification. The inner
Sure.
partitions were not thermally insulated to begin with.
no,
Is
no,
that
no,
what you're saying?
no, they were not thermally insulated. Only this container, this setting, the entire
The outside is only thermally insulated.
thermally insulated. Yeah. So the end.
So, are we like saying that the heat from one partition can go to the other partition, even though the like energy can transfer, but
Yes.
all right.
Yes. Energy can transfer. Essentially. Yeah.
Okay.
But
Mhm.
so you just look at this entire system, you can say that delta U is equal to 0. The net energy is 0. And such that we observe these behaviors. I think I'm hearing echo. Anyhow. So we look at this such that there is a thermodynamic equilibrium, which is an essential important part in all this thermodynamics laws. And what is this thermodynamic equilibrium? It essentially means when the net energy is 0, that energy but there is a change from of the system from here to here and here. So there must have been some quantity related to this material gas that would have been conserved in all these three settings, and that is we take is a temperature, such that the internal energy is a function of temperature alone. We can just remove all other parameters like the P, V, and as such. So this is essentially what I wanted to impart from the Zeroth law and the thermodynamic equilibrium. And then the first law is, if you see, you take the same kind of container and you use even some kind of springs within it, these springs with forces and which can be compressed such that they have a difference in lengths, and this gas with some kind of piston such that you can change the pressure and volume of this. As long as this is thermally insulated, it's all mechanical work that is going on. And we can say that energy change will be equal to delta W, will be some kind of force times displacement plus pressure times change in volume of this. But as soon as you remove the thermal insulation from this, you take the same thing happening. If suppose in this scenario, I take the force and pressure first, or the pressure, and I take the similarly X or the volume, and I begin from some initial condition and I reach some final condition, we can observe that this will obey. I do not care about how I go from this initial path to final path, but this will be obeyed. But the same thing, if this is no longer thermally insulated and I try to do the same thing, no longer delta U is equal to delta W. So that is essentially, as ma'am was trying to say in the previous picture, an exchange of heat, which can happen from the mechanical work. So for that, you need to make use of heat exchange plus the entire mechanical work. This can account for all the heat exchange, and this can account for all different kind of mechanical work, like the spring, oscillator, or some kind of gas in the container. And the third law essentially tells you that this is some function of temperature, and there must be an analog with this force times displacement. And so we have this entropy sitting here from this. And essentially, so this black body radiation, we'll be not using any mechanical work. We'll be only seeing such that these, we'll see oscillators, which is an imaginary oscillators, which are just functions of temperature and entropy. Something analogous to this mechanical kind of oscillators, but now we see that they're just a function of temperature and entropy. So we'll try to explain how these oscillators can be described.
Yeah, maybe you can define entropy first for people who
Yes, which will be the part of the process for it. So entropy, that will be my next. Yes. So I take a simple, since this was aimed at a high school approach, I wanted to take a simple approach to explain how this entropy can be defined. And so suppose I take a two-sided dice, which is essentially a coin, but I like to keep going it as seeing at dices, and I flip it 2 times. Yeah, or I take two-sided dices and I flip them. I get such that all the possible configurations are this essentially. And now if someone asks you what will be the least amount of information that needs to be used to send this flip to information about the two flips to someone else, that can be defined from, the information can be obtained from something like log base 2 base 2. I'll tell it, the base 2 will be the basis of information. For instance, zeros or ones, which is the commonly used base in computers, and 2 power 2 is this 2 dices with 2 sides. So this n will be the number of dices n, and m will be the sides of the dices. For instance, if I want to share this information of 1 1, it will be something like 0 0, or 2 2, it will be 1 1, where I impart 1 as 0 and 2 as 1. And similarly, if I go for some 2 4-sided dice, which will be essentially log base 2 in the same base of zeros and ones, it will be, oh sorry, yes, 4 sides power 2. So this will be 4 essentially. So what this means is, whatever be the, these are the different possible outputs you can get from this 2 4-sided dice. If I have a method of sending these messages like this, as long as I have this method, I can send it just with 4 bits of information. Oh yes, this is something like 4 bits of information. And this,
Venkat, what did you call I? I mean, what was the terminology you used for I?
information.
Information.
Yes. So, and then, yeah, this information can be related to the entropy in my language from a simple constant. So this is how I'll start defining entropy, which is a constant times log G. G is the number of possible configuration I can have in this any system. So now we'll try to see this G in different situations. For instance, a simple case like we have this m sides and n, oh, n is number of sides. M sides and n number of dice. You can take the entropy as k log m power n. Simple as that. But now we'll be interested in a scenario where we'll take m-sided dice, but the n dice are identical. That will be the most interesting identical nature in this kind of partition function, because now why I take identical dice or something is, I'll try to relate this dice with these light particles which are coming out of this different black bodies. And so what an important thing in this light particles is they are identical in nature. A light particle which can take millions of years for us to travel from, for instance, sun. So what happens in sun is, a sun is a densely packed gas essentially. So in this room, if the source from a tube light or something, the light does not take too much time to travel. But since sun is essentially a densely packed structure, it takes a lot of oscillations within the sun and to come out. And so it can take around millions of years. So, and we'll not be able to differentiate between a light particle which we get from sun or from this tube light essentially. They're completely identical. So I try to use this identical dice picture to try to relate how to get this Z for the black body. Yes. So for identification of this Z. Essentially, I'll just make this problem simpler and simpler. First, I'll make it simple, where we take two M-sided dice, which is essentially such that we need to take two, as we saw in the previous page, the Z had two positions, and you can fill from 1 to M, 1 to M. And this can be easily obtained from, you take MC2. C is the combinatorial, whatever is used in probabilities. And this MC2 means that you take any two sides from this dice and you place them. For instance, it can be 1, 2, or anything, 4, 7, or any as such. And then you have that corresponds to this. And then you have MC1, which means I take just one, I can repeat it. So why am I doing this? Might be your question. So what happens is, I'll again try the same structure. For the Z, the different kind of we get. No, it's one comma. And here it's yeah. So the same thing, whatever happens. So I can see it like this is a for light particle and this is a light particle. And we are interested in such a configuration where a sum of this must be different. So this sum and this sum are the same. This sum and whatever here, 1, 3, this sum will be the same. So this is the only way you can arrange all the different unique configuration to get the G for this two M-sided identical dice. And I next go for 3 M-sided identical dice, which can be seen from such that I need to fill 3 places and their sum should be unique. So that can happen only from MC3, where I take 3 different things and I place them, plus 2 times MC2, this is Z, which is essentially I take, for instance, some 8 and 7 and I replace 7 or I replace 8. This is what I mean for this. Plus I take MC1, which is essentially I take one thing and I repeat for all three places. And I can keep on going like this for 4 M-sided dice. So I'm hope
Venkat, you are
yes.
going a little too fast even for me.
Oh.
So is it possible
Sure.
to like at least simplify? I realized that for counting the like whatever you're writing for Z, you are having like Z basically, you are
Yes.
counting only the unique configurations.
Yes.
So first of all, you can clarify why only the unique, why the degeneracy has been removed, like
why it has been removed. So I explained it for the simple case of 2 M-sided dice initially, and this will be the entire configuration.
yes.
And so essentially I'm taking care that I'll have only this diagonal terms. Diagonal
And the lower diagonal. So basically your
diagonal.
matrix, if I think of it as a matrix, it's a symmetric
Yes.
matrix and you are just taking
Yes.
the independent. But why are we giving away the other ones? Like in defining entropy,
Yes.
why are you not counting the states which are degenerate? Let's say, I don't know. I mean,
Yeah, and I don't know what is the degeneracy yet. So I'll just say that I'm not interested in identical dice. So if I throw two dice and I get 2, 1 or 1, 2, I won't be able to differentiate from what dice I'm getting 2 and from what dice I'm getting 1. So that's how I look at this identical dice. I'll try to relate it with the
okay, maybe
identical.
maybe it
Yeah.
will get clear later on, but I mean, I will think that whatever is contributing, even if you throw the dice and even if you cannot distinguish between which dice gave you what,
Yeah.
it's a possibility still, right?
So yeah, we are talking about classically that I'll be able to differentiate it. Yeah. But let us forget that I'll be able to distinguish it. I'm
Mhm.
taking their indistinguishable, which is
Okay. Mhm.
classically. I mean, it's hard to follow classically, but I'm trying to take a picture of dice so that later I'll be able to explain it for the light particles. Essentially, I try to explain for the identical light particles, but this is classically indistinguishable. Two
Yeah, I
dice are
guess it
indistinguishable.
has to do with the definition. Like maybe if you can later on clarify more on the definition of what you mean by yeah, like what you mean by like entropy and what does Z account for. Maybe it will clarify like why only the unique distribution.
No,
But I don't know.
For me, entropy is, according to me, information, just information of whatever. It can be even identical dice. Even if I take m power n, it can be just k log m power n, as I said. And it's just information that is required to send this m dice of m dices in some basis, as I was trying to say here. So in basis of zeros and ones, it will just be for a two-sided dice, two-sided dice, it will just be 2 for me. It can be identical or non-identical.
Yeah, it
And that
can be,
is
right?
entropy.
That is what I'm saying.
Yeah,
Like
yeah,
it
yeah.
can be identical or non-identical, but now
Exactly.
for getting the Z, you are actually
Yeah.
excluding all the identical ones. You're just
Yes.
keeping the unique one. And that is what I was asking, like why it is being removed. But maybe it will clarify itself. So let's proceed. And
So yes, I'll try to see a pattern in this G if possible, so that I can take this nice simple procedure. So again, we have this 4 positions, and I need to fill the such that the sum will be unique. And so that will have something like MC4 plus 3 times MC3 plus 3 times MC2 plus MC1. So this again, as you saw, can be any 1, 4, 8, 9 as such, 4 different unique things that can account for all this MC4. And this can be accounted such as repeating one thing, any 1, 1, 4, 8 twice, and such that 1, 4, 4, 8 and 1, 4, 8, 8 as such. And similarly, this can account if I take any 2, and I can account for all this 4, 4 or 1, 1, 1. Yes, I'm right. 4, 4. And this is all 4 are the same again. So this can account for all the things which are same. And so I can keep on going like this and hopefully see the pattern in a Z.
okay, I take back. You are counting everything. So I
Yes,
take
I'm counting. I'm counting it. Yes. So yeah, yes, this I've done this multiple times. Hopefully, yeah. And so I go for the 5 m-sided dice, and I'll hopefully get a similar kind of expression. And yes, so one who is not aware of much in maths may not find a pattern here, but oh, sorry. This is nothing but something like the Pascal's triangle, which is happening here. If one tries to observe it carefully. So what is this? Pascal's triangle. This Pascal's triangle has a pattern where the sum of this both will give you this, and sum of these both will give you this, and you can keep on going like this. So I'll be able to write the next term as 1, 5, 10, 10, 5, 1. I can keep going. This is the Pascal's triangle that will keep going. And I know, so now I know all the terms. So I can now generalize this for m-sided identical dies. Okay, now ma'am says it's not, it can be, it's indistinguishable. We cannot even distinguish these different dices. And so this will be, I'll get a expression for this G. So, and I can get an expression for this G essentially. And I can even write it as a nice summation form. And using a Vandermonde's identity as such, I can write it as a simpler form even. And so this is all, that is the G from this m n-sided identical dice that I'll get. This is, if you know the combinatorial, you can write it as this. Yeah. So this is essentially the G, whatever is we are interested in the Blackbody. Now, yeah, that might be very a leap that I'm taking, why this G is the Blackbody. So hopefully I'll be able to explain this. So as I was saying, we are interested in just a scenario like this, where there are these oscillators, n oscillators, whatever the springs, I was trying to see the mechanical springs, and these, whatever frequencies you get from these oscillators, as I was saying, the light particles can be associated to a frequency which is lambda, and also lambda times mu is some constant. This mu are essentially light particles with some nu and some lambda. These, as I said, were identical because of whatever I was saying, the light particle, you will not be able to distinguish light particles from two different sources. So that is why this Z is what can give you the essentially the Blackbody radiation as such. So any clarifications so far? Any doubts? Or I think I've been going too fast, or I don't know whether. Yeah.
Maybe a little bit too fast in the sense that you did not connect, like connect between the Blackbody.
Blackbody, yes, still so.
So I think you said somewhere that it was equal to the information times something.
Yeah, the K, some constant K.
Yeah, I mean, I think it's okay. Like, I mean, unless Sharish wants to clarify something more.
Anything that is missing, you feel?
I'll wait for some more time.
Sure. Okay. So, yeah, this is the more again this gets more complicated, I suppose. And essentially, I'll have the entropy of this n oscillators, and I'll take it to be simply n times S, and I'll take the energy of this n oscillators to be n times U, where U is the oscillator energy of each oscillator. And also I'll be taking the total sum will be some energy times epsilon. Epsilon will be the individual energy of all these light particles, and M is the total sum. So essentially we are distributing this energy between these n oscillators using this kind of partition function. And that's why I was telling the sum and such. And this epsilon is again taken to be h times nu, which is again something done by Planck, essentially, that each energy of the light particle will be proportional to the frequency of this with a constant. And so with this, I'll just move forward. And yeah, now we take such that this energy is levels, whatever the different energy levels are really high, and also the number of oscillators are really high. With this, we have to use something called as Sirlings Approximation. Where you need to take, you get such as this. This is an idealization, again, which is useful in some sense, where you take such that n factorial is just n power n, when n is much larger than 1. And so now I know the definition of the entropy. And I can get an expression like this. And essentially, I just need to use some algebra to relate all these quantities. Yeah. And yeah, that's a little bit of algebra that is happening in between. And finally, you can get using this. It's the energy of this or each oscillators h times nu. And we saw already that delta S, wait, U is 1 by T that I'll be using. And so I can do the trivial differentiation of this quantity with respect to U to get 1 by T as the same constant time h nu log of 1 plus h nu by U. And I can do some algebra again, and I can get the energy of each oscillator as, yeah.
So question, Venkat,
Yes, definitely.
how did you get 1 plus V over epsilon? What was the argument there?
1 plus U.
Like there was a connection between the number of M and this, correct?
Yes, yes, yes. And so m by n is essentially u by epsilon. M
And
is the different energy levels that we have for the oscillators which are possible, and n is the number of oscillators.
I see. Okay.
Yeah.
And U is
Energy per oscillator.
Yeah, I see. Okay.
Yes, and yeah, I definitely hope there are questions. Yeah, because
Okay.
there was this flow in my mind. I don't think I got the flow, whatever I was expecting in my mind, completely imparted to everyone for the first time who are seeing all this. Yeah, and the audience seemed to be very wide, and I don't know, yeah, what went through them. So yes, any question
okay.
is fine with regard this derivation or the Blackbody as such. Yes.
Well,
And
I mean,
yes,
if you could, yeah, I don't know. Like, okay, so I can tell first and then Shaish can tell, like,
sure.
you may have a specific question. If you could summarize, basically emphasizing on the definition of entropy, what do you mean by black body radiation here? And like, I think other stuff I can get, like, it's all depending on partition function. So basically how you count
Yeah.
your, yeah. So just a tiny bit of summary to 1 minute summary in the end.
I feel the important connection I made between the entropy and the black body radiation, whatever I've been handling, is in this page where I take n-sided n identical dice, and I get a partition from, okay, I should not use the term body, the number of configurations possible for that such a scenario, and that is the entropy for essentially the black body that I'm using. If you see it, yeah. So that is all. You just need to take some kind of probabilistic situation where you are having m-sided n identical dice, and you find the different possible configurations for that, which will be, yeah, which is quite easy, and you'll get the partition from, you'll get the entropy of this entire black body. Yes.
Yeah, Shajesh, maybe you were asking something.
No, I'm good. Yeah.
Okay. Yeah.
Yeah, so like I can maybe go like further down in definition. What do you mean by entropy? For example?
Yes. This is all is my definition of entropy.
Yeah, but it is a very mathematical definition of entropy. What do you mean by entropy physically?
Yeah, so all I can say is the different possible configurations. I mean, the information here in this situation, how I took it is the information that is required to send from one person to another to get this number of possibility, different possible outcomes. That's all is the entropy here. So like I was saying, in the if you see it as bits, zeros and ones, for if you flip a coin, two-sided coin n times, it is just n, because you can just get it, everything in the terms of zeros and ones. If it's a heads, it would have been 0. If it's a tails, it would have been 1. And I can say, if I get heads 0, tails heads, you can keep saying for n times. So that is all the entropy, definition of entropy in my scenario here.
Mm-hmm.
And just for the system, irrespective of what kind of boundary it is, it always gives the
Boundary.
same.
Yeah, I don't know. There are no boundaries here. in my definition.
It does not depend on the shape of the boundary, right?
No, it's not, there's nothing. The system is just oscillators or springs, as I was trying to say, which have this temperature dependence on them. And
No, you do
entropy
have a
dependence.
boundary in the sense that you defined your box to be isolated. If you don't make the system isolated, probably it will be hard
Oh.
for you to think in terms of entropy of the entire system. So there is a definition of boundary. It's just that
Yes.
when you think of it in terms of information, then you completely forget about that because you're not
Boundaries. Yeah,
worried
yeah,
about
yeah.
the boundaries.
Yeah.
And
Yes, there are some kind of boundaries, I suppose, but
yeah, and that's where like probably it is, it would be nice to probably relate what it means by information entropy and thermodynamic entropy, like a connection
Yeah.
between them. That might help. Like I can see the connections, but I
yes,
think
yes,
it's
yes,
not
yes.
very like easily
Yeah.
conveyed.
That I did not want to begin here. The relation between whatever entropy I'm trying to say and the thermodynamic entropy, which is defined in the second law. Yeah, that I did not want to even attempt here. I thought it would take a lot more time.
Yeah, but while you were doing it, like I was really thinking, so in a way, when we count for the partition function, we are always doing an upper bound, right? On this, like whether you consider the counting of all the states and whether you consider the putting the Stirling approximation, it's like going on the upper bound all the time, right?
Yes, yes, yes. Yeah, that's what I was trying to impart in the first page itself, that all these laws, thermodynamic laws, will boil down from all these microscopic conditions only when you take this limit, when you take large degrees of, I should not use the term, large number of particles.
Mhm. Yeah,
Yes.
maybe I will think about a little bit later on about like what it means to
Yes, sure. One more
have a,
audience member has already seen a lot of this. My guide Sankarnarayan sir, yeah, yeah. We have discussed a lot about this, I suppose. Initially, very initially, 4 years back. Yeah,
Mhm.
yeah. This dice picture also seemed nice to me, and it was not. I did not find any literature which seemed to have this kind of dice partition functions that were happening.
You said this was originally whose work? Like, I mean, I don't remember. I think.
Yes, that is, if you see, yeah, originally done by Planck in 1901. Yes.
Venkat?
Yes. Yes, sir. Yes, sir. Yes, sir.
Yeah. Can you go to the last slide?
Oh, last page. Yeah.
Okay. So you are calculating entropy in terms of U. Then finally, you are using this relation delta S by delta U is equal to 1 by T.
Yes.
From there, you are getting an expression for U in terms of frequency, right?
Yes, 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 yes.
Okay. And this is supposed to be the curve which you drew in the beginning.
No, 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 no. No, no, no. Sorry. Sadly, I don't go to even that part. Yes.
Okay. Okay. What is this? What is this formula and what is the curve which you mentioned in the beginning?
Yeah, yeah. For that, I have to do a bit of more maths where I have to integrate for all possible.
Okay. Okay. Oh.
Yeah. Yeah, I didn't want to use integration and anything as much. Yes. But you can do this very easily. Yeah.
So what is this U here? It's the energy of the system, which has
energy of an oscillator. Energy of an oscillator. Average energy of an oscillator.
Energy of an oscillator. Okay.
Yeah, one oscillator. I didn't want to again use this.
Okay. From here you have to derive. From here you have to derive the Planck's radiation. Is it?
Yes, yes, yes. It's just integration, but
yeah. Okay. Okay. Fine.
No.
And Yeah, I understand that, you are using a nice description in terms of oscillators and counting the oscillators and
Yes.
so on. Probably to, have a good, what is the insight on the entropy. Of course, you tried your best to, in terms of
Yes.
counting.
Yes.
Yes. And I understand that you also avoided some thermodynamic arguments and so on, right?
Yes. I've already.
Yeah, but you can't escape using this relation like delta S by delta U equal to 1 by T.
Yeah,
It's
it's
a
just
thermodynamic relation.
Yeah, it's a thermodynamic second law. Yes.
Yeah. Correct. Yeah, the thing is, it's actually a bit hard on this subject to take on to the students, but
Yes.
still you
Yes.
tried your best. Yeah,
Yeah.
okay.
Yes.
I
So,
think,
yeah,
it would be better if we start with more intuition towards entropy and thermodynamics. Then if you do this, that
Yeah.
would be a fantastic sequel
Yes.
for people of different background will be able to appreciate
Yeah.
what Planck has done, right?
Yes. One
Yeah.
has to, even this, whatever I used, the S is equal to
Yeah.
was too much for in a single talk, I would say. Yeah. But I just,
Pretty interesting approach, but the only
Yes,
thing is for the beginners, it might be slightly difficult to comprehend or something. Yeah, but the
Yes.
arguments are very interesting. Yeah, okay.
Yeah. And yeah, so I just want to say that from probabilistic arguments alone, okay, I should not say that, but probabilistic how probability is important in a high school. I mean, we try to study probability so much. We use this NC2s and we do so many problems with dice, but we don't know where we use it. But it's
Correct.
important in a physical situation, in a black body. Yes.
Yeah,
So
that's right.
Yes.
Can you just elaborate the two kinds of expression you gave for U?
Oh, sure.
Somewhere down, one
Yeah,
you wrote in terms of N, one you wrote in terms of M. No? Yeah.
So that is something like, this is average energy per oscillator. So there are n oscillators, and this is the total energy of the oscillator. And I also that from all this picture, from oscillators picture, you get out the energy in some energy levels, which are m, and it is discrete epsilon. So that is why we are able to write un is m times epsilon. And m will be the maximum energy in this different energy levels.
Okay. So we should be able to connect N and M in this definition to the dice and the number of sites, right? Number of dice and number of sites. Okay.
Yes. Again, I'm not saying that number of sites is that's why I differentiate. This is small m and this is capital M, because here small m is the number of dice which can be. There are a lot more small m's, but capital M is the maximum energy possible. That's all.
I see.
Yeah. If you try to see in this picture, you will have a term which will have.
What did you mean to say? Like capital M is total what?
Energy levels of this oscillator.
Total energy levels.
Yeah. But here, small m, there can be a term which will have, in this case, 4 small m's. It will be 4 times m, and in n case, there will be n times m. And so we should not compare this small m with this capital M. That's what I wanted to find the differentiation.
So in the textbooks, have you read the Berkeley physics course for undergraduates?
Yes, I think I've seen the textbook for the Berkeley. They use this argument, right?
They use the probabilistic argument to define
but
entropy.
they go to Bose-Einstein condensation.
No, not that quickly. It's undergraduate, right? It's beginning undergraduate, the first course in thermodynamics.
Okay, I should not say Bose-Einstein condensation. Sorry, Bose-Einstein statistics. Yes,
Yeah,
both in
I-
syntax statistics. Yeah, yeah.
I studied long back, so I cannot tell, but I remember that the entropy was defined with microstates, and
Yeah,
it was done with the probabilistic argument.
Yeah, that is again simple approach where you can see it in terms of this. If you have some m energy levels of sets, you need m-1 sticks to differentiate this. And this n will be this whatever balls and sticks. So these balls are identical and these sticks are identical. So to arrange these balls and sticks, essentially you can get m-n-1 factorial by m-1 factorial. This because there are identical sticks and n factorial. This is much more simpler way of seeing this. But yes, I did not want to take this because this is essentially, I think, the Bose-Einstein statistics will give you. Yeah. Oh, you also have GI degenerate energies. Yeah, but yeah. I don't want to go into that.
So by measuring the black body radiation, can we say anything about the intrinsic statistics of the information?
Where are we measuring it from?
Suppose I have the spectrum,
Yes. Yes.
or let's say if I were to have electrons do the same thing, instead of having photons, we have an electron gas. And let's have a similar system where there is a cavity and electrons being Fermi Dirac. And if I were to have an intensity versus frequency plot, will there be a difference,
I don't.
or is it
I don't.
too odd efficient?
No, it's. I think there are many factors playing a role. When I take this limit m greater than 1, n greater than 1, a lot of information has been lost from this jet, I feel. Yeah, this approximation, we lose a lot of information already.
It's Stirling approximation. So you're
Yeah.
saying that information will be lost then?
I don't know. That's why I was thinking. I don't know. I think we need to change the configuration of the system and keep changing. I don't think it will be possible. Keep making it smaller. I don't think. I don't know. Somehow we have to try to get back this relation of m and n. But I don't think we can make any predictions about the statistics from the whatever distribution output we get. And as I was saying, this is all what we can say about this system. That's all. We don't know what is actually happening in the system. This jet is not complete picture. I mean, yeah, there will be Z0 plus Z. If you try to see actually there will be much more statistics that may be relevant if you go to a different situation. But here all we require is this Z. Is what I'm thinking.
Good.
Yes.
Yeah, I just want to reiterate the same thing which I raised a little while ago.
Okay.
You try to avoid detailed mathematics behind the whole thing, but still you have to use all these mathematical tools.
Yes.
Again, from the expression of U, which is supposed to be the average energy of an oscillator, right?
Yes.
Okay, so from the average energy of an oscillator, can you tell what is the procedure to get that curve so that if any youngsters are there, they'll be benefit.
procedure to get, yeah, essentially we have to integrate in all the possible, this gives you already the information about what is the energy at each frequency. You need to integrate it over all the different possible frequencies to get the whatever energy density actually required. So, yeah.
Venkat, don't go through the integration process, just write the result
Oh,
for the
right,
curve.
there is yeah. Yes, that is possible. Yeah, that is. Okay, I need to differentiate this. Yeah. This is the energy density, whatever the Planck's Blackbody that we are interested in.
Yeah, okay. This is what you plotted. The first.
Yes. Now this will be U star and this will be 1 by mu. This is good, I suppose.
Venkat?
Yes, sir. Yes.
Yeah, okay, yeah, fine.
Yeah.
I'm just wondering,
Yeah.
yeah, this is nice to finally you got the curve which you began with, right?
Yes.
Okay. You have written down delta S by delta U is equal to 1 by T.
Yes.
So can we also think of this expression for the definition of temperature statistically or something? So this looks like we have an alternate definition for temperature, right? Looks like.
No, I don't think we can. Yeah. So I can say U is a function of temperature, S is a function of temperature, but I do not know how we can define temperature from U, change in entropy, change in internal energy.
Here 1 by T is rate of change of S with U, something like that, right?
Yes.
So that can also be thought of as an alternative definition for or statistical definition for temperature or something.
Oh, I don't think so. We can use it. I mean, just because we can have dx by dt as velocity. Oh, yes. Yes.
Because usually we use the word temperature in a loose sense, right? So this could be one way of looking at temperature more closely, sort of.
No, but yeah, this is not the entire. Oh, yeah, this is not the entire thing, right? The entire thing is. That's also mechanical. Yeah.
No, this is fine. What you have written is fine.
Yeah.
So what I'm saying is that this can,
in my initial scenario, what will be now happening? I cannot define temperature now, right? That's what I initially took the Zeroth Law to explain that net internal energy is zero in this case.
I mean, the change in energy with entropy is temperature, something like that.
Yes, yes, yes. But I'm saying this is always not true, right? I mean, it should be always
It is
true.
true.
Only then.
It is true. It is true.
But now I took a scenario where internal energy is 0. But then I won't be able to define this, right? Yeah.
It is actually.
I think the third law, I'm just trying to think.
No, this is actually a partial derivative. What you wrote is actually a partial derivative, but
I'm not sure about this.
because it also has some quantity which is constant somewhere while taking the partial derivative. I don't remember what it is.
Okay. Maybe we'll discuss this further.
Yeah, we'll discuss it.
Yeah,
Okay, yeah.
sure. Yes. Yeah. So I think Shajeshwar is occupied with something else.
Yeah.
Yeah.
Probably.
Okay. So,
Uh,
and
but that's a good question to ask. Like if you have an isolated system,
yeah.
then you are saying that total energy is not changing.
Yeah.
But that, like, I mean, the definition, like that is a true definition also. Like,
This is more. These are path-dependent quantities. This is more pure definition of the first law, whatever, which I didn't want to use.
yeah. Maybe some point you can take it up on this, this relation
Yeah.
here and define
Yeah.
entropy.
That would be a good thing. Thermodynamics by itself will require a quite bit of time to go through actually, yes. I'm just using the laws here, which I did not give a reason why how I'm using them.
So maybe like just a totally different thought here on the last expression that you have wrote, where actually the Planck's constant was introduced. And
Yes.
and I thought that like these were the experimental results, right? These were the curves were the experimental results.
Yes.
And experiments always have uncertainties.
Yeah.
Right? So they will be like some sort of uncertainty related with each curve. Why H became like so fixed a number? Like it was introduced to describe the curves, right? Like discretization of the energy level, radiation basically, that they are released in packets.
Yeah.
I mean, I never read the details of the experiment myself, like always read the theory about the Blackbody, Planck's Blackbody radiation curves. But I'm just wondering, like, if you have, what kind of uncertainty was there so many years back, and how was he able to make this number H so precise?
I think you could get it so precisely because it was such a small number. It's such a small number in any units you take.
Yeah, but it is not like, I mean, he is giving us like some significant figures here.
Yeah,
like,
he gave
not only
precision of only 2 in the first paper. He gave it precision of only 2. which is less, I would say. He gave something like H is 6.55 times 10 power minus 27 in Earth seconds. He just gave question of 2. I think this would have been why we now have more question, I suppose, in this H. The initial experiments would have led him to have only 2 digits precision in this.
Yeah, and even that feels like too much of a precision.
Yeah,
But
yeah,
anyway.
exactly. That's true. That's true. That's true. Actually, yeah.
Like if you're confident about, like you are giving 3 significant figures, there is no plus minus, I guess, to value of H.
Yeah.
Anyway, that's a good talk, Venkat. I mean,
Okay,
it's
thank you.
entropy is a good topic.
Yeah.
Maybe we should get into like little bit more
Yes.
detail.
Yeah.
I think you were
Hopefully.
trying to convey a lot in short time.
Yeah. That's a message.